Weak queries kill recall before ranking even starts. This is the pattern you'll be able to implement by the end, which drafts a hypothetical answer from a weak query and uses it to retrieve and re-rank matching texts. I'm Professor Pi, teaching Search and IR with Simple Python. Search systems often break when the user types one or two vague words. The retriever never sees the intent, so relevant passages never surface. HyDE stands for Hypothetical Document Embeddings. It asks a model to imagine an answer first, then uses that imagined answer to find documents. Haystack is a practical pipeline library that wires together lexical search, dense vectors, and re-rankers without building everything from scratch. Intuitively, HyDE aims to turn a weak question into a richer text that looks more like a real answer. Think of a user asking just latency. A normal lexical search looks for the word latency. HyDE would generate a sentence like, "Latency in our service caused by network retries and slow DB calls," and use that to fetch documents that actually discuss mitigation. Strengths are higher recall for thin queries and better coverage. Weaknesses are extra compute for generation and embedding longer text. We will build a tiny pipeline that shows three things. First, a baseline lexical retriever over 3 toy documents. Second, a dense embedding retriever that understands meaning. Third, a HyDE style expansion that re-ranks candidates with a stronger model. You will see how adding a short hypothetical answer moves a weak query closer to the right documents before re-ranking. Now we start the first demo. This snippet sets up a tiny Haystack BM25 retriever baseline over 3 toy documents and issues a short query. The in-memory document store holds the texts, and the list comprehension builds Haystack document objects quickly. After writing them to the store, the BM25 retriever attaches to it and performs sparse lexical search. The variable Q captures a weak single-term query that often struggles in production. The retrieve function returns ranked documents with a score indicating term matching strength. Increasing top K shows more candidates at the cost of additional scoring work. The printed top text and BM25 score confirm that the latency-related snippet is retrieved from purely lexical overlap. Next, we add a semantic baseline to compare what dense matching finds. This example switches to Haystack's EmbeddingRetriever to add a dense semantic baseline. The object wraps a SentenceTransformers model that embeds both documents and queries into the same vector space. Calling update embeddings stores vector representations in the same in-memory store so dense lookups can run efficiently. With the vague query weak Q, retrieve returns the nearest document by cosine similarity, even if the exact words do not match. Raising top K increases recall by surfacing more candidates to consider later, with extra retrieval time and memory for vectors. The printed top text and similarity show semantic matching works on the short query. Now, we craft a hypothetical answer and see how that changes retrieval. This code crafts a HyDE-style expanded query by composing a short, plausible answer-like phrase, then searches with Haystack's EmbeddingRetriever. The list terms collects concepts that a good answer might mention for API latency mitigation. The variable HyDE concatenates these into one coherent hypothetical statement, which often moves the query closer to the document manifold in vector space. The retriever then embeds this richer text and returns the top semantic match. Using a more targeted or longer hypothetical can raise recall further, but increases retrieval latency slightly due to longer text embedding. The printed similarity shows the expanded query strengthens the match. Next, we merge candidates and apply a stronger reranker to pick the best answer. This snippet pools candidates from the baseline dense query and the HyDE expanded query, then re-ranks them with a Haystack SentenceTransformers ranker. The lists dense K and HyDE hold top results from each retrieval pass. The dictionary merged deduplicates by content, producing a compact candidate set canned. The cross-encoder ranker consumes the original weak query and rescores each candidate using a deeper pairwise model via predict. Increasing top K in retrieval tends to improve re-ranking quality, but may slow the pipeline due to more cross-encoder evaluations. The printed cross-encoder score confirms which candidate wins after a stronger semantic judgment. Now, we package the flow into a reusable function to run end-to-end. This snippet wraps a tiny HyDE retrieval routine into a reusable function that stays entirely in Haystack. The function HyDE search builds a concise hypothetical answer from the weak query, then runs 2 retrievals with the EmbeddingRetriever. The dictionary deduplicates candidates to keep the pool small and stable. The SentenceTransformers ranker rescores using the original query, returning the best matching content and the pool size for visibility. Expanding the hypothetical phrase or increasing retrieval top K often boosts recall, but may add latency from more embeddings and cross-encoder passes. The printed top text and pool size show an end-to-end baseline result. In a real project, this maps to a user-facing query layer. The hypothetical answer generator can be a small language model. The embedding store can move from in-memory to FAISS for larger corpora. The re-ranker stays as a final accuracy boost before the answer is shown. Recap. It is a HyDE retrieval pattern that generates a plausible answer to strengthen a weak query. Use it when queries are short or ambiguous and you need better recall before re-ranking. Caveat. It adds generation and embedding costs, so measure latency versus the recall gains. Next step, scale this pipeline with an ANN index like FAISS and tune its nList and nProbe to balance recall and latency. If short, practical IR helps, subscribe and watch the IR videos.